What if I told you that the very fabric of reality around you isn't quite what it seems? That the universe we live in bends, twists, and warps in ways so strange, even the wildest science fiction barely scratches the surface. Picture this. You're standing still, but right now, you're hurtling through space at unimaginable speeds, caught in a cosmic dance with stars, galaxies, and the invisible threads of space-time itself. This isn't just theoretical physics, it's the mind-bending truth of our existence. And today, we're diving headfirst into its deepest mysteries. Think back to the most jaw-dropping moments from movies like Interstellar or Star Trek, where black holes distort time and wormholes bridge galaxies in an instant. Those ideas didn't just come from thin air, they're rooted in the real, awe-inspiring science of space-time, a concept so revolutionary it changed our understanding of the universe forever. Einstein's theory of relativity showed us that space and time aren't separate entities but woven together into a single, flexible fabric. And just like a trampoline with a bowling ball in the center, massive objects like stars and planets create ripples in this fabric, bending the rules of reality as we know them. But here's where it gets even wilder. Space-time isn't just a backdrop for the cosmos, it's an active player, shaping everything from the orbits of planets to the very flow of time itself. Imagine being an astronaut near a black hole, where time slows to a crawl compared to Earth, or pondering the possibility of wormholes, cosmic shortcuts that could, in theory, connect distant corners of the universe. These aren't just thought experiments, they're real phenomena that push the boundaries of what we thought possible. And in this video, we're uncovering 30 astonishing facts about space-time that will leave you questioning everything you thought you knew. From the eerie effects of time dilation to the mind-blowing implications of parallel universes, each revelation is a piece of a puzzle that's still being solved by the brightest minds in science. So buckle up, we're about to take a journey through the most extraordinary corners of reality, where the rules of physics as we know them begin to unravel, and the true nature of the universe reveals itself in ways you've never imagined. Einstein didn't just revolutionize physics, he rewired our entire understanding of reality when he revealed space-time isn't just emptiness but a dynamic, stretchable fabric. Picture a trampoline stretched taut, perfectly flat until you drop a bowling ball onto it. The ball sinks into the surface, creating a curve that pulls everything nearby toward it. Now replace the trampoline with the fabric of the universe and the bowling ball with a star or planet. That's gravity in action, not some mysterious force reaching out across space, but objects bending space-time itself, telling anything nearby how to move. The heavier the object, the deeper the dent, and the stronger its gravitational pull. This idea was the heart of Einstein's general theory of relativity, which showed that mass and energy don't just exist within space-time, they shape it. Think of Earth orbiting the Sun. It's not being magically tugged along by invisible strings. Instead, the Sun's immense weight warps space-time around it like a whirlpool, and Earth simply rolls along the curve of that distortion, like a marble circling the rim of a funnel. Even light, which has no mass, can't escape this bending, proven during a solar eclipse in 1919 when stars appeared slightly out of place because their light was curved by the sun's gravity. But here's what really twists the mind. Space-time isn't just bending in 3 dimensions like that trampoline. It's a 4-dimensional fabric with time woven into it just as tightly as length, width, and depth. A black hole doesn't just distort space, it warps time too, slowing it down so drastically that near its edge, seconds stretch into years elsewhere in the universe. This isn't speculation. GPS satellites orbiting Earth have to account for these tiny time distortions caused by our planet's gravity, or their navigation data would drift off by miles. The universe isn't just sitting there. It's a living, flexing stage where every star, every planet, even you and I, leave our own faint ripples in the cosmic fabric. Ever wondered if time itself could stretch and squish like taffy? It turns out gravity doesn't just pull objects, it drags on time too. Imagine two identical clocks, one placed on Earth's surface and the other launched into orbit. Over time, the clock in space would run slightly faster than its Earth-bound twin. This isn't a flaw in the machinery, it's gravitational time dilation, a real-world quirk of Einstein's relativity where time slows down in stronger gravitational fields. Near a black hole, the effect becomes extreme. A single hour for someone hovering near its edge could mean decades or even centuries passing elsewhere in the universe. This bizarre phenomenon isn't just theoretical. GPS satellites orbiting 12,000 miles above Earth have to account for these tiny time shifts, or their navigation data would drift by about 6 miles per day. Here's why: because they're farther from Earth's gravity, their clocks tick 40 microseconds faster each day than those on the ground. But relativity also says their high speed slows time down by 7 microseconds daily. The net difference, 33 microseconds. Without correcting for this, your phone's GPS would guide you into a field instead of a freeway exit. The implications stretch beyond technology. If humans ever orbit a black hole like in Interstellar, time dilation could separate explorers from everyone they've ever known. A 5-year mission near its edge might mean returning to an Earth that's aged centuries. Even on smaller scales, your head technically ages faster than your feet by a fraction of a nanosecond over a lifetime because it's slightly farther from Earth's gravitational pull. Time isn't the rigid, universal constant we once thought. It's fluid, bending under the weight of the cosmos, proving reality is far stranger than fiction. What if you could step through a cosmic door and emerge halfway across the universe in an instant? That's the tantalizing promise of wormholes, hypothetical tunnels through the twisted fabric of space-time that could connect distant points like a shortcut through the cosmos. Picture folding a piece of paper so two dots at opposite ends touch. A wormhole would be the needle pricking through both layers, creating a bridge where a journey of billions of light years collapses into a single step. Einstein's equations of general relativity actually allow for such bizarre structures. In 1935, he and physicist Nathan Rosen theorized that black holes might not be dead ends but gateways, linked to their counterparts by bridges through space-time, later dubbed Einstein-Rosen bridges. But here's the catch: these tunnels would be wildly unstable, snapping shut faster than light could traverse them. To keep a wormhole open long enough for anything to pass through, you'd need something truly exotic, matter with negative energy, which repels gravity rather than attracting it. This isn't just sci-fi fluff. Scientists have actually observed fleeting hints of negative energy in quantum experiments, where particles briefly borrow energy from the vacuum of space itself. But sustaining enough to stabilize a wormhole, that's like trying to build a suspension bridge out of soap bubbles. Even if we could, the risks are staggering. One miscalculation and the tunnel could collapse into a black hole, or the very act of stepping inside might trigger a fatal feedback loop of radiation. Yet the allure persists. Wormholes wouldn't just defy distance, they'd twist time, potentially allowing travel to the past or future. Some theories suggest they're microscopic, peppered through the quantum foam of space-time, while others imagine civilizations advanced enough to engineer them like interstellar highways. Until we uncover physics beyond Einstein or stumble upon a naturally occurring wormhole, they remain a breathtaking what-if, teasing us with the possibility that the universe's most distant corners might be closer than they appear. Here's something that sounds impossible: galaxies racing away from us faster than the speed of light. How can that happen if Einstein's relativity says nothing can outpace light? The answer lies in the fabric of space-time itself, because it's not the galaxies moving through space, but space expanding between them. Imagine dots on a balloon. As you inflate it, the dots don't move, yet the space between them grows. Now scale that up to cosmic proportions, where the balloon is the universe, and those dots are entire galaxies being carried apart by the stretching of space-time. This expansion isn't just happening, it's accelerating, thanks to a mysterious force called dark energy. Think of it as an anti-gravity effect woven into the vacuum of space, pushing galaxies apart faster and faster. By some estimates, dark energy makes up 68% of the universe's total energy, yet we've never directly detected it. Its presence is only revealed by the universe's runaway growth, like footprints of an invisible giant. Here's the twist: relativity's speed limit only applies to objects moving through space, not to space itself stretching. So while a galaxy can't zoom through space faster than light, the space between us and that galaxy can expand so rapidly that it effectively recedes at superluminal speeds. This creates observable horizons, regions of the universe so distant their light will never reach us because the space between is growing too fast. We're left with a cosmic puzzle. If dark energy keeps strengthening, could it one day tear apart galaxies, stars, even atoms? Some theories suggest a Big Rip scenario, where space-time stretches so violently that everything, planets, molecules, the fabric of reality, is shredded. But for now, we're left watching the universe's grand acceleration, a reminder that the rules of physics still hold surprises beyond our boldest imaginations. Time travel isn't just the stuff of science fiction. It's happening right now, every single day, just not in the way you might expect. While we can't whip up a DeLorean with a flux capacitor, the universe has already built its own time machine, and it operates on two simple ingredients: speed and gravity. Take the famous twin paradox, a thought experiment that's been proven real down to the millisecond. Imagine one twin blasting off on a near-light-speed rocket while the other stays on Earth. When the traveling twin returns, they'd be younger than their Earth-bound sibling, not by days, but potentially by years. That's because time slows down for anything moving close to light speed, a phenomenon called time dilation. This isn't just theoretical. Astronauts aboard the International Space Station experience it on a tiny scale. Orbiting at 17,500 miles per hour, they age about 0.005 seconds slower every 6 months compared to people on the ground. But crank that speed up to something like 99.9% of light speed, and the effect becomes staggering. A 5-year trip for the traveler could mean decades or even centuries passing back home. You wouldn't just see the future, you'd skip ahead in it, like jumping chapters in a book. Gravity can pull off the same trick. Picture orbiting a black hole where space-time bends so sharply that time nearly grinds to a halt. Spend 1 hour in that extreme gravity, and years could whip by elsewhere. The craziest part, this isn't breaking physics, it's Einstein's relativity in action. Time isn't a universal metronome ticking the same for everyone. It's more like a river flowing at different speeds depending on how fast you're moving or how close you are to something massive. So while we can't hop backward in time, at least not yet, the future is wide open. The only catch: you'd have to leave everything behind. A round trip near light speed might land you in the year 3000, but everyone you knew would be long gone. That's the bittersweet trade-off of cosmic time travel. The universe lets you cheat time, but never the loneliness that comes with it. Black holes don't just bend space-time, they can spin it like a cosmic tornado, dragging the very fabric of reality around them in a dizzying whirlpool effect called frame dragging. Picture stirring honey into tea. As the spoon rotates, it pulls the liquid into a swirling motion. Now replace the spoon with a black hole spinning at nearly the speed of light, and the honey with space-time itself. This isn't a gentle tug, it's a violent distortion where the black hole's rotation yanks nearby space, and anything in it, into a spiraling dance. Einstein's equations predicted this phenomenon decades ago, but it wasn't until 2004 that scientists found direct proof. NASA Gravity Probe B missions spent over a year orbiting Earth with gyroscopes so precise they could detect shifts thinner than a human hair over a mile. The result, the probes measured a minuscule but undeniable twist in space-time caused by Earth's rotation, a weaker version of what happens near a black hole. Now imagine scaling that up to a black hole like Gargantua from Interstellar, where frame dragging becomes so extreme it creates an ergosphere, a region outside the event horizon where space-time is whipped into such a frenzy that nothing can stand still. Not even light. Astronomers have spotted real-world evidence of this around supermassive black holes, where swirling jets of plasma stretch thousands of light years into space, twisted by the black holes spin like water from a garden hose. The implications are staggering. Frame dragging could theoretically warp space-time so severely that it opens paths to time travel or naked singularities, black holes without event horizons. For now, these remain speculative, but one thing's certain: black holes aren't just cosmic vacuum cleaners. They're the universe's ultimate puppeteers, pulling the strings of space-time itself in ways we're only beginning to comprehend. The Big Bang wasn't just the birth of matter and energy. It was the moment space-time itself flickered into existence. Forget the idea of a colossal explosion erupting in some pre-existing void. There was no outside, no empty stage for the universe to expand into. Instead, space and time unfolded from an incomprehensibly hot, dense point called a singularity, stretching and cooling like rising bread dough. This means the Big Bang didn't happen somewhere, it happened everywhere, because everywhere was created in that instant. We've actually caught an echo of this primordial event, the cosmic microwave background, a faint glow permeating the entire sky. Picture it as the universe's baby photo, taken when it was just 380,000 years old. Before that, the cosmos was so hot and dense that light couldn't travel freely. It was a searing fog of plasma. But as space expanded and cooled, protons and electrons combined into atoms, releasing light that's been stretching across the eons. What started as blinding gamma rays has cooled into microwaves over 13.8 billion years, now just 2.7 degrees above absolute zero. Here's what's wild: the cosmic microwave background isn't perfectly smooth. Tiny fluctuations in its temperature, variations as small as 1 part in 100,000, reveal the seeds of all cosmic structure. Those microscopic density bumps grew under gravity's pull, becoming galaxies, stars, and eventually us. It's like finding fingerprints in the fabric of space-time, evidence of quantum jitters from the universe's first trillionth of a second. But the deepest mystery lies in what triggered the Big Bang. Some theories suggest a quantum fluctuation in a void, while others propose collisions between higher dimensional branes. One thing's certain: the Big Bang wasn't just an event in space-time, it was the moment space-time began ticking, a cosmic clock starting at zero. And every second since, from the formation of atoms to the birth of galaxies, has been scribbled into the expanding parchment of the universe. Zoom in far enough, past atoms, past quarks, down to scales so small a single grain of sand would dwarf them by a factor of a trillion, and the smooth fabric of space-time dissolves into chaos. This is the quantum foam, a seething, frothy mess where the universe itself seems to boil with uncertainty. At these unimaginably tiny distances, space-time isn't a tranquil pond. It's a stormy ocean with virtual particles popping in and out of existence and wormholes flickering open and shut like bubbles in a soda. Here, the very concepts of here and now lose meaning as space and time fluctuate wildly, defying all our everyday intuition. The quantum foam arises from a fundamental clash between two titans of physics, quantum mechanics and general relativity. Quantum mechanics rules the realm of the very small, where particles behave like waves, and certainty gives way to probability. General relativity governs the vast cosmic dance of planets, stars, and galaxies, where space-time bends under the weight of matter. But when you try to merge them to describe gravity at microscopic scales, the equations explode into nonsense. infinite energies, collapsing dimensions, and paradoxes emerge, screaming that our understanding is incomplete. Imagine trying to measure the surface of a bubbling pot of water with a ruler. At larger scales, it might seem flat, but zoom in, and the bubbles make any precise measurement impossible. That's the challenge physicists face with quantum foam. The Planck length, about 10 to the power of minus 35 meters, marks the scale where space-time's smoothness shatters. Smaller than this, the very idea of distance becomes meaningless as quantum fluctuations warp geometry itself. Even time stutters, with chronons, hypothetical fragments of time, potentially ticking irregularly like a broken stopwatch. Some theories suggest the foam is threaded with microscopic wormholes or extra dimensions curled up like invisible origami. Others propose that space-time is built from discrete atoms of geometry, much like a digital image emerges from pixels. But without a theory of quantum gravity, a unified framework bridging the quantum and cosmic realms, the foam remains a tantalizing enigma. Experiments to probe it directly would require particle accelerators the size of galaxies, so for now, we're left with mathematics and imagination to navigate this turbulent underworld of reality. One thing's certain, beneath the calm surface of the universe we see lies a frenzy of quantum chaos, reminding us that space-time is anything but simple. We think of time as a foundational part of reality, an ever-ticking backdrop against which the universe plays out, but what if it's just an illusion? Some of the boldest theories in physics suggest time isn't fundamental at all, but something that emerges from deeper, more primitive layers of reality. Much like temperature isn't an intrinsic property of matter, but a collective effect of countless atoms jiggling. Take loop quantum gravity, a leading contender for unifying quantum mechanics and general relativity. In this framework, space-time isn't smooth and continuous but woven from tiny, indivisible loops. Think of it as a cosmic mesh where each thread carries a quantum of area or volume. Here's the twist: time doesn't appear in the core equations. Instead, it emerges from how these loops interact, like watching a movie frame by frame until motion seems to flow. It's not that time disappears, it's more like realizing the second hand on a clock is just a side effect of gears turning unseen beneath the face. This idea isn't entirely new. Even in thermodynamics, we see how macroscopic properties like pressure or heat arise from microscopic chaos. No single molecule has a temperature, but together their motion creates the sensation of warmth. Similarly, time might be a collective effect, a cosmic temperature born from the frenetic interactions of quantum space-time. Some models even suggest that near a black hole's singularity or at the Big Bang's instant, this emergent time could dissolve entirely, leaving physics to play out in a strange, timeless landscape. The implications are staggering. If time isn't fundamental, then concepts like before and after might only make sense in certain contexts, like how wetness means nothing to a single water molecule. It challenges everything from causality to the arrow of time, hinting that our experience of past, present, and future could be a cosmic sleight of hand. For now, these ideas remain at the frontier of theoretical physics, but they force us to ask, is time the stage or just a player in a much deeper game? We're used to living in a world of 4 dimensions, 3 of space and 1 of time. But what if the universe is hiding layers we can't see? String theory, one of the most ambitious frameworks in physics, suggests space-time might actually have 10 or even 11 dimensions, with the extra ones curled up into unimaginably tiny shapes, like a garden hose viewed from far away. At a distance, it looks like a simple line, but up close you realize it's a cylinder. These hidden dimensions could be as small as the Planck length, 1 billion trillion times tinier than an atom, explaining why we've never noticed them. The math behind this idea isn't just speculative, it's a necessity. When physicists tried to reconcile quantum mechanics with gravity, their equations kept breaking down until they added these extra dimensions. Picture a violin string vibrating at different frequencies to produce distinct musical notes. In string theory, the fundamental particles we know, electrons, quarks, photons, are like those notes created by tiny strings oscillating in higher dimensional space. But here's the catch: for the theory to work, those strings need more room to vibrate than our familiar 4 dimensions provide. Scientists aren't just theorizing, they're hunting for proof. The Large Hadron Collider, the world's most powerful particle accelerator, has been searching for clues like missing energy that could hint at particles drifting into extra dimensions. Some models even suggest gravity might appear weaker than other forces because it's leaking into these hidden layers. Imagine water seeping through microscopic cracks in a pipe. Gravity could be doing the same, dispersing its strength across dimensions we can't perceive. The implications are staggering. If extra dimensions exist, they could explain mysteries like dark matter or even open portals to parallel universes. Some theories propose that what we call a black hole might be a bridge to a higher dimensional space, while others suggest these dimensions could unravel the singularity at the Big Bang. For now, they remain just beyond our grasp, folded into the fabric of reality so tightly they're like shadows on the wall of a cave. But if we ever uncover them, it would rewrite not just physics, but our very understanding of existence. Ever notice how certain events seem irreversible? Drop a glass and it shatters instantly, but no matter how long you wait, the pieces never leap back into your hand perfectly whole. This isn't just a quirk of fragile objects, it's a fundamental feature of the universe called the arrow of time, and it's tied to a law so absolute that physicists consider it nearly sacred, the second law of thermodynamics. At its core, this law states that entropy, a measure of disorder, always increases in a closed system. Think of it as cosmic wear and tear. Energy tends to spread out, systems get messier, and structure decays into chaos over time. Here's why this matters for time's one-way street. Imagine a box of gas molecules. At first, they might be neatly clustered in one corner, a state of low entropy. But left alone, they'll always spread to fill the box evenly, maximizing disorder. Reverse the process, though, and you'd need to carefully orchestrate every molecule's path, a statistical miracle so unlikely it's practically impossible. That's why time feels directional. We remember the past because it's a state of lower entropy, and the future is where entropy grows, carrying us toward ever greater disorder like a cosmic current. This explains everything from why ice melts in your drink to why you can't unburn a log. But there's a twist. The laws of physics themselves don't actually forbid time from running backward. At the microscopic level, particles don't care about past or future. If you filmed 2 atoms colliding and played it in reverse, you couldn't tell the difference. The arrow of time emerges from statistics, the overwhelming likelihood that systems evolve toward disorder, not away from it. So why does the universe have such low entropy in the past to begin with? That's one of cosmology's biggest mysteries. Some theorize the Big Bang set the clock ticking by creating an ultra-ordered state, like winding up a spring. Others ponder whether multiple arrows of time could exist in other regions of space-time, where entropy flows differently. But for us, time's direction is written in broken glass and fading stars, a reminder that the universe marches toward chaos, and that's why yesterday stays behind us, forever out of reach. Einstein predicted them a century ago, but even he doubted we'd ever catch one. Ripples in space-time itself, sent hurtling across the cosmos by the most violent events in the universe. Then, on September 14, 2015, humanity's most sensitive instrument, LIGO, caught the faintest whisper of a disaster that happened 1.3 billion years earlier. 2 black holes, each 30 times heavier than the Sun, spiraling into each other at half the speed of light. In their final moments, they unleashed a gravitational wave, a distortion in space-time so powerful it stretched and squeezed Earth by 1,000th the width of a proton as it passed. Think of space-time as the surface of a pond. drop a pebble and ripples spread outward. Now replace the pebble with a black hole collision and the pond with the fabric of reality. These waves aren't made of matter or energy but of pure geometry, compressing space in one direction while stretching it in another. By the time they reached Earth, the distortion was so tiny it took LIGO twin detectors, with laser beams running through 2.5-mile-long vacuum tunnels, to spot it. The lasers detected a shift in length smaller than 1/10,000th the diameter of a proton, a feat like measuring the distance to Alpha Centauri down to the width of a human hair. The discovery wasn't just a triumph of engineering, it opened a new window on the universe. Before 2015, astronomers relied almost entirely on light-visible X-rays, radio waves, to study the cosmos. Gravitational waves let us hear the universe, sensing cataclysms invisible to telescopes. Since that first detection, LIGO and its European counterpart, Virgo, have caught waves from neutron stars colliding, black holes merging in mismatched pairs, and even mysteries that defy explanation. One event, dubbed GW 1924-25, might have been a black hole swallowing a neutron star or something entirely unknown, but the real revolution lies ahead. Future observatories like the space-based LISA will detect lower-frequency waves, revealing supermassive black holes dancing at the hearts of galaxies. Some theories suggest we might even catch echoes from the Big Bang, ripples from the birth of space-time itself. Gravitational waves aren't just signals, they're the universe's way of letting us listen in on its most secret conversations, written not in light but in the shuddering fabric of reality. If you could zoom in on space-time like a microscope approaching infinite magnification, you wouldn't find smooth, unbroken fabric. You'd hit a fundamental limit, a cosmic pixel, beyond which reality itself becomes grainy. This smallest possible unit of distance is called the Planck length, roughly 1.6 times 10 to the power of -35 meters. To grasp how absurdly tiny that is, imagine shrinking a proton, already 1,000,000 times smaller than an atom, until it's as small compared to the Planck length as a proton is to you. At this scale, the universe stops playing by the rules we know. Space-time isn't continuous, it's more like a digital image where reality is built from discrete, indivisible chunks. This idea shakes the foundation of classical physics. Einstein's relativity treats space-time as a smooth, stretchable sheet, while quantum mechanics deals with particles and waves. But when you try to merge them, the math explodes into infinities at the Planck scale, screaming that something's missing. Theorists propose that space-time might be woven from quantum loops or spin networks, tiny, interconnected threads vibrating with energy, forming a dynamic mesh. Picture a soccer ball's surface. From afar, it looks smooth, but up close you see the stitched hexagons. The universe might work the same way, with Planck-length pixels as its stitching. Here's where it gets wild. If space is pixelated, time might be too. Just as a movie is made of frames, the flow of time could tick in Planck time increments about 10 to the -43 seconds. In this view, the present isn't a fleeting instant but a series of cosmic snapshots, updating like a quantum flipbook. Some models even suggest that at this scale, cause and effect might blur, with events happening out of sequence until they average out into the smooth time we experience. Evidence is indirect but tantalizing. When physicists analyze high-energy cosmic rays, some appear to interact with space-time as if it's grainy, like light scattering through frosted glass. Others hunt for Planck-scale noise in gravitational wave detectors, hoping to catch space-time fizzing at the smallest scales. If confirmed, it would mean reality is fundamentally digital, not just matter and energy, but the very stage they perform on. The catch, probing this directly would require particle accelerators bigger than our galaxy. So for now, the Planck length remains a frontier, teasing us with the possibility that the universe runs on code we've yet to crack. A photon doesn't just move at light speed, it exists outside of time entirely. Imagine you could shrink yourself down and hitch a ride on a beam of light racing from the sun to Earth. From your perspective, the 8-minute journey wouldn't feel like 8 minutes or even 8 seconds. It would happen in an instant, as if the moment you left the sun's surface, you were already here. That's because at the speed of light, time dilation doesn't just slow time down, it grinds it to a complete halt. For a photon, the entire universe is frozen in a single, eternal snapshot. This mind-bending consequence comes straight from Einstein's special relativity, which tells us that time isn't absolute but stretches or squeezes depending on your speed. The faster you move through space, the slower you move through time, like some cosmic trade-off where velocity steals ticks from the clock. But light doesn't just push this effect to the limit, it breaks it. At light speed, the equations collapse into a singularity of timelessness. There's no before or after for a photon, just an unchanging now that spans its entire existence. Here's what's even wilder. This isn't just theoretical. We've observed it indirectly through particles called muons, cosmic ray byproducts that rain down on Earth. Normally, muons decay in microseconds, but when they're zipping through our atmosphere at nearly light speed, their clocks run so slow they survive long enough to reach the ground. Now crank that speed up to 100% light speed, and the muon's clock would stop entirely, just like the photons. So what does this mean for the universe? It reveals a staggering asymmetry in reality. While we watch a photon travel billions of years across space, for the photon itself, every star it passes, every galaxy it streaks through, all of it happens in zero time. The universe's entire history could flicker past like frames in a single, frozen instant. It's a reminder that time isn't just relative, it's deeply personal, woven into the very fabric of motion. And for light itself, the cosmos isn't a story unfolding. It's a single, infinite moment, forever suspended at the speed of now. The universe might just be the ultimate magic trick, an illusion where everything we see, touch, and experience could be nothing more than a cosmic projection. This is the heart of the holographic principle, a radical idea suggesting our three-dimensional reality is actually encoded on a distant, two-dimensional surface, like a movie being played back from the surface of a DVD. The concept emerged from an unexpected place, the study of black holes. When physicists calculated how much information a black hole could hold, they hit a paradox. The entropy, or hidden information inside a black hole, seemed to scale not with its volume, but with the area of its event horizon. It's as if all the complexity of everything that ever fell in was compressed into a flat, ultra-dense script painted on the boundary. Imagine stepping into a room with walls covered in microscopic text, every word describing the position, momentum, and properties of objects inside. Now scale that up to cosmic proportions. The entire universe, from swirling galaxies to the neurons firing in your brain, could be written in symbols on some unimaginably distant surface. This isn't science fiction. The math suggests that just as a hologram encodes a 3D image in a 2D film, the universe might store its information at the edges of space-time. Even you, right now, might be a kind of avatar emerging from data etched on the cosmological horizon billions of light years away. Black holes are the key to this mystery. When matter vanishes past an event horizon, it doesn't just disappear, its information gets scrambled and smeared across the surface. This led physicist Gerard T. Hooft and later Leonard Susskind to propose that perhaps all physics is fundamentally about information exchange at boundaries. Think of it like a video game. What you experience as a rich, interactive world is just the output of code running on a flat screen. The holographic principle flips reality inside out, suggesting that depth, texture, and even time might be emergent properties of something far simpler. But how could this possibly be tested? Surprisingly, there are hints. Some versions of string theory mathematically equate higher dimensional universes with lower dimensional quantum field theories, a duality called ad s/CFT correspondence. It's like discovering the blueprint for a skyscraper also perfectly describes a painting of that skyscraper. Even the behavior of quark-gluon plasma in particle accelerators echoes predictions from holographic models. If the principle holds, it could mean the universe is fundamentally pixelated, with each Planck-sized area of the cosmic horizon holding just one bit of information. Your entire life, every memory, sensation, and moment might be written in vanishingly tiny etchings on the edge of everything. So the next time you look up at the stars, consider this wild possibility. You're not just observing the cosmos. You are the cosmos, a flickering pattern in a grand hologram, where the real story is unfolding not in the space around you, but on some distant, invisible surface where all of reality is being projected into existence. Black holes swallow everything, even light, but what if somewhere in the universe there's a cosmic fire hose blasting out matter and energy instead? That's the bizarre idea behind white holes, black holes' hypothetical twins. If a black hole is a one-way street where nothing escapes, a white hole would be its mirror image, a region of space-time where nothing can enter, only eject. Picture a black hole running in reverse, like hitting rewind on a video of a collapsing star. Instead of pulling material in, it violently expels it. The math makes this tantalizing. Einstein's equations don't care which way time flows, so a white hole is just a black hole with time flipped. In theory, it could be the other end of a wormhole or a black hole's afterlife. Some models suggest that when a black hole dies through Hawking radiation, it might rebound as a white hole, spewing back everything it ever consumed. But here's the catch: while black holes form naturally from collapsing stars, white holes would need some kind of cosmic reset button, violating the second law of thermodynamics. Nature prefers entropy to increase, not reverse. Even if they existed, white holes would be fantastically unstable. The moment any matter or energy touched their boundary, calculations suggest they'd collapse right back into a black hole, like a soap bubble popping at the slightest touch. That hasn't stopped astronomers from searching, though. Some have speculated that mysterious gamma-ray bursts, flashes of energy brighter than entire galaxies, could be white holes erupting into existence, if only for a split second. Others wonder if the Big Bang itself was a white hole event, a singular outburst of space-time from an infinitely dense point. For now, white holes remain a cosmic what-if, a reminder that the universe's rulebook might have pages we haven't flipped yet. They're the ultimate cosmic rebels, defying the natural flow of time and entropy, and that's exactly why they fascinate physicists. Whether they're real or just mathematical ghosts, white holes challenge us to think differently about the fabric of reality, where even the most outrageous ideas might hide a kernel of truth. What if our universe is just one bubble floating in an endless cosmic foam, with countless other universes, each with their own unique laws of physics bubbling up beside it? This isn't the plot of a sci-fi epic. It's a serious scientific idea rooted in inflationary cosmology, the theory that our universe underwent a mind-boggling expansion in the first fraction of a second after the Big Bang. But here's the twist: inflation might not have stopped everywhere. Some regions of space-time could still be stretching exponentially faster than light, creating pockets where new universes pinch off like soap bubbles separating from a frothy sea. Picture a pot of boiling water on a stove. Each rising bubble is its own self-contained universe, with its own physics, constants, and even dimensions. In some, gravity might be 10 times stronger. In others, electromagnetism could be too weak to hold atoms together. Some might be barren, with no stars or planets, while others could harbor alien forms of life thriving under conditions we can't even imagine. This is the multiverse in its most extravagant form, not just parallel timelines, but entirely separate cosmic domains where the fundamental rules rewrite themselves. The math behind this is surprisingly sturdy. Inflationary theory suggests that quantum fluctuations in the early universe could create false vacuum regions where space-time keeps expanding at breakneck speeds. These zones become nurseries for new bubble universes, each tunneling out of the inflationary background like sprouts bursting through soil. String theory adds another layer, proposing that different bubble universes could represent distinct solutions to its equations, each a unique way to compactify hidden dimensions. But how could we ever detect these other universes? Some theories suggest that if two bubbles collided, the shockwave might leave an imprint on the cosmic microwave background, a kind of bruise on the sky. Others speculate that strange anomalies in the distribution of galaxies or the behavior of dark energy could hint at a neighboring universe pressing against ours. For now, the evidence is elusive, but the sheer possibility reshapes our cosmic perspective. If the multiverse is real, then every conceivable reality might exist somewhere, not just in theory, but in the infinite froth of space-time itself. Imagine a snowflake that doesn't just repeat its pattern in space but in time, a structure that cycles endlessly without energy, like a perpetual motion machine that somehow sidesteps the laws of physics. This isn't science fiction, it's a time crystal, the first new phase of matter discovered in decades. While ordinary crystals, like diamonds or quartz, have atoms arranged in repeating spatial patterns, time crystals flip the script. Their atoms oscillate in a predictable, repeating rhythm over time, even in their lowest energy state. They're like cosmic clocks that tick forever without being wound up, defying everything we thought we knew about equilibrium. The wildest part, time crystals aren't just theoretical. In 2017, researchers at Harvard and the University of Maryland brought them to life inside quantum computers and supercooled diamond lattices. By using lasers or microwave pulses to nudge entangled ions or nitrogen vacancy centers, they created systems that locked into rhythmic patterns like a pendulum swinging at fixed intervals, but without any energy input after the initial kick. It's as if you pushed a child on a swing once and they kept swinging perfectly for years, never slowing down. What makes time crystals so revolutionary is how they cheat thermodynamics. Normally, systems settle into equilibrium. Think of hot coffee cooling to room temperature. But time crystals never equilibrate. Their atoms oscillate indefinitely, locked in a dance that doesn't dissipate energy. This breaks time translation symmetry, a fancy way of saying physical laws usually work the same whether you're observing them now or an hour later. Time crystals, though, pick a favorite rhythm, creating a structure that's tied to time itself. Potential applications sound like they're ripped from a futuristic tech catalog. Quantum computers could use time crystals as ultra-stable qubits, immune to the decoherence that plagues current systems. Their precise rhythms might lead to hyper-accurate atomic clocks or sensors so sensitive they could detect gravitational waves in a desktop experiment. Some even speculate they could model exotic physics, like wormholes or black hole dynamics, in lab-scale experiments, but the deepest implication is philosophical. Time crystals hint that there might be entirely new phases of matter hiding in plain sight, realms where time itself becomes a building block. They blur the line between the abstract and the tangible, proving that even in the most controlled labs, the universe still has surprises up its sleeve, ones that don't just exist in space but in the very fabric of time. Is the universe shaped like a sheet of paper, a balloon, or a Pringles chip? The answer might determine everything from whether space goes on forever to how the cosmos will eventually end. For decades, scientists have scrutinized the faint glow of the cosmic microwave background, the oldest light in existence, searching for clues about the geometry of reality itself. The data suggests space-time could be flat, meaning parallel lines never meet, and the universe stretches infinitely in all directions. But there are other possibilities, like a spherical cosmos, where space curves back on itself like the surface of a planet, or a hyperbolic, saddle shape, where space flares outward in a dramatic, warped expanse. A flat universe fits neatly with our current understanding of cosmic inflation, that rapid expansion in the first moments after the Big Bang. Measurements from satellites like Planck show space-time's curvature is astonishingly close to zero, like a pool table so perfectly leveled a marble wouldn't roll even an inch over billions of light years. In this scenario, the universe could keep expanding forever, growing colder and darker as galaxies drift apart like lonely ships in an ever-widening sea. But close to zero isn't zero. Some models suggest that if space-time has even a whisper of positive curvature, like a giant four-dimensional sphere, everything might eventually reverse. Galaxies would stop fleeing, pulled back by gravity in a big crunch, collapsing all of existence back into a singularity. Then there's the saddle-shaped universe where space-time curves negatively, like a horse's saddle or a crisp potato chip. Here, parallel lines would diverge wildly, and the cosmos would stretch itself thin at an accelerating rate. Distant galaxies would vanish over the horizon of perception, their light stretched beyond detectability, leaving future astronomers with a sky nearly empty of stars. The cosmic microwave background holds subtle hints like the way temperature fluctuations are distributed across the sky, but the evidence isn't definitive. Some anomalies, like the cold spot, a bizarrely chill region of space, have even sparked wild theories. Could it be a bruise from a collision with another universe, warping our local geometry? The stakes couldn't be higher. A flat universe suggests dark energy will keep driving expansion until atoms themselves tear apart. A spherical one offers the dramatic possibility of rebirth, a cyclical cosmos where every ending births a new beginning. And a saddle shape, that's the ultimate runaway universe where space-time itself becomes a funhouse mirror, distorting reality beyond recognition. For now, the data leans toward flat, but the question isn't settled. After all, we're like ants trying to map a continent by studying a single grain of sand. The full shape of the cosmos might still be hiding in the wrinkles of space-time we've yet to unfold. The universe as we know it could vanish in an instant, not with a bang or a whimper, but with a silent, unstoppable rewrite of reality itself. This unsettling possibility is known as vacuum decay, a hypothetical doomsday scenario where the very fabric of space-time tears up its own rulebook. Think of reality like a ball resting in a valley, a stable, low-energy state we call the true vacuum. But what if our valley is just one dip in a vast cosmic landscape, and somewhere out there, a deeper, more stable valley exists? If triggered, a tiny patch of space could quantum tunnel into that lower energy state, creating a bubble of true vacuum where the laws of physics as we know them cease to apply. This bubble wouldn't just sit there, it would expand at the speed of light, rewriting everything it touches. One moment you're sipping coffee, the next atoms no longer hold together, stars dissolve into quantum froth, and the fundamental forces like gravity and electromagnetism snap like overstretched rubber bands. The worst part, you'd never see it coming. The bubble's edge moves too fast for any warning, erasing the old universe so completely that even the concept of erasure loses meaning. It wouldn't just destroy matter, it would replace physics itself with something alien and unknown. The trigger could be almost unimaginably small. A single high-energy particle collision in some distant lab, a random quantum fluctuation in deep space, or even the natural aging of the universe might nudge reality over the edge. Physicists call our current state the false vacuum because it's stable for now, like a pencil balanced on its tip. But given enough time or the right disturbance, it could tip into the true vacuum, unleashing a cosmic reset button. Oddly enough, this isn't pure speculation. The Higgs field, which gives particles their mass, might exist in such a precarious state. Calculations suggest its current energy level could be metastable, like a frozen lake thick enough to skate on, but with patches already thinning. If confirmed, our universe wouldn't just be mortal, it'd be inherently unstable, a ticking time bomb with no countdown. Yet there's a strange comfort in this fragility. If vacuum decay hasn't happened in 13.8 billion years, the odds are staggeringly in our favor. Some theories even suggest an earlier collapse could have jump-started our Big Bang, meaning we might be living in the aftermath of someone else's cosmic reboot. For now, vacuum decay remains a chilling what-if, a reminder that the universe's deepest laws might be as temporary as a sandcastle at high tide. What if the Big Bang wasn't the beginning, just a reboot? The idea that time might stretch backward beyond that fiery instant shakes the foundations of modern cosmology. Most of us grew up hearing the universe burst into existence from a singularity, but some theories suggest it could be part of an endless cycle, like a phoenix dying and being reborn in an eternal loop. Take the Big Bounce, for instance. This radical reimagining proposes that before our expanding universe, there was a contracting one, a cosmos that collapsed inward until it reached a critical density, then bounced outward in the cataclysm we call the Big Bang. Picture a cosmic accordion squeezing tighter and tighter before springing back open, resetting the clock with each rebound. The math behind this isn't just speculative. Loop quantum gravity, a leading contender for unifying quantum mechanics and general relativity, suggests that at incredibly high densities like those near the Big Bang, gravity becomes repulsive rather than attractive. Instead of collapsing into an infinitely dense singularity, the universe would hit a quantum wall, reversing its collapse into expansion. It's like compressing a spring until it suddenly pushes back with enough force to launch a new cosmic epoch. Evidence might even be hiding in the cosmic microwave background, where slight anomalies in temperature fluctuations could be echoes of a pre-Big Bang universe. Then there's the cyclic model, championed by physicists like Paul Steinhardt and Neil Turok, which paints an even grander picture. Here, our three-dimensional universe exists on a membrane or brain floating in higher dimensional space. Collisions between our brain and a neighboring one could trigger repeated Big Bangs, not as resets but as cosmic rejuvenations. Each collision would release unimaginable energy, forging new matter and radiation while preserving subtle traces of the previous cycle. Imagine two sheets of paper smacking together in a windstorm over and over, each impact birthing a new universe. The implications are staggering. If time existed before the Big Bang, then the arrow of time, the one-way march from order to disorder, might not be universal. Some regions of reality could run backward, with entropy decreasing instead of increasing. Black holes in a previous cycle might have left faint imprints in our universe's structure, like cosmic fossils embedded in the distribution of galaxies. Even the laws of physics could evolve across cycles, with each bounce tweaking constants like the speed of light or the strength of gravity. But how could we ever test these ideas? Some theorists hunt for patterns in the large-scale structure of the universe, like concentric rings in galaxy distributions that might be remnants of pre-Big Bang events. Others look for gravitational waves from the earliest moments, which could carry whispers of a prior contraction. The challenge is separating these signals from the noise of our own universe's chaotic infancy. Whether a bouncing cosmos or colliding brains, these theories force us to confront a humbling possibility. Our universe might be one chapter in an epic with no beginning or end. The Big Bang could be less of a birth and more of a turning point, a hinge between eras in an infinite, unfolding story where time itself is just another player on the stage. Somewhere in the depths of space, hidden behind the thick curtain of our own Milky Way, lies a cosmic mystery so vast it's tugging entire galaxies toward it against the unstoppable tide of universal expansion. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it warps the paths of hundreds of thousands of galaxies, including our own. Right now, the Milky Way, along with Andromeda and countless other galaxies in our local supercluster, is racing toward this unseen behemoth at over 2 million kilometers per hour, caught in a river of space-time that flows against the current of the expanding universe. The Great Attractor isn't just massive, it's invisible to our telescopes, lurking in the zone of avoidance, a region of the sky obscured by the dense gas and dust of our galaxy's disk. Its true nature remains veiled. What little we know comes from observing its gravitational fingerprints, the way it bends light from distant galaxies, the peculiar motion of galaxy clusters pulled like leaves in a cosmic whirlpool, and the eerie uniformity of their trajectories, all pointing toward a single, unseen focal point. Based on these disturbances, scientists estimate the Great Attractor's mass could exceed tens of thousands of Milky Ways crammed into a space just a few 100 million light-years across. But here's the twist: this gravitational titan might not be the final destination. Recent observations suggest the Great Attractor itself is being pulled towards something even larger and more enigmatic: the Shapley supercluster, a megastructure containing nearly 10 times the mass, lying another 600 million light-years beyond it. It's as if we've discovered a colossal waterfall in space-time, only to realize it's just one cascade in a vast intergalactic river system whose true source remains uncharted. What could explain such a staggering concentration of mass? One theory posits dark matter, the invisible scaffolding of the universe clustered in densities beyond our comprehension. Others speculate about exotic phenomena like cosmic strings, defects in space-time left over from the Big Bang that could warp gravity on galactic scales. Or perhaps the Great Attractor isn't a single object at all, but a knot where multiple filaments of the cosmic web intersect, funneling galaxies together like roads merging into a highway. The deeper mystery is why this region holds such gravitational sway in the first place. According to standard cosmology, the universe's expansion should dilute these vast overdensities, making them rarer as time passes. Yet the Great Attractor defies expectations, challenging our models of large-scale structure. Some even wonder if it's a sign of something stranger, a flaw in Einstein's relativity, or evidence of a multiverse tugging at ours from beyond. For now, the Great Attractor remains a cosmic riddle, its secrets buried behind the Milky Way's dusty veil. But new telescopes like the James Webb Space Telescope and next-generation radio observatories are peering through the obscuration, mapping the hidden currents of space-time with unprecedented clarity. Each discovery brings us closer to answering the haunting question: what unseen force is rewriting the fate of our corner of the universe? Whatever it is, one thing's certain: the cosmos still has ways of reminding us how much we have yet to learn. Einstein called it spooky action at a distance, a phenomenon so bizarre it made him question the very foundations of quantum mechanics. Today, we know it as quantum entanglement, and it might just rewrite our understanding of space-time itself. Picture two particles born from the same quantum event, forever linked no matter how far apart they drift. Change the spin of one, and its partner instantly flips too, as if they're sharing a hidden frequency across the cosmos. This isn't just theoretical. Physicists have demonstrated it over distances exceeding 1,200 kilometers, with particles responding to each other faster than light could travel between them. Here's what rattles scientists: this instantaneous connection seems to bypass space-time entirely. In our everyday world, information can't outpace light, its relativity's ultimate speed limit. But entangled particles don't appear to communicate through space at all. They act as if distance doesn't exist, like two sides of a single coin flipped in the void. This has led some theorists to propose that space-time might not be fundamental, but an emergent property of something deeper, a cosmic mirage woven from quantum threads we've yet to untangle. Skeptics fought hard to find flaws, proposing loopholes that could explain the results without invoking spooky action. Maybe the particles were secretly pre-programmed, or our measurements were biased. But recent experiments have slammed these doors shut. In 2015, a Dutch team executed a landmark, loophole-free test using diamonds separated by over 1 kilometer, with their entangled electrons responding in perfect sync. Even more striking, a 2017 Chinese experiment used satellites to entangle photons across record distances, eliminating the possibility that hidden signals could travel through Earth's atmosphere. The verdict: entanglement is real, and it defies any classical explanation rooted in space-time as we know it. This throws a wrench into how we perceive reality. If entangled particles can coordinate without traversing space, does that mean space-time is just a stage, not the director? Some interpretations, like the holographic principle, suggest our three-dimensional world could be a projection of entangled quantum data stored on a two-dimensional surface. Others propose that entanglement creates wormholes in space-time's fabric, linking particles through microscopic bridges. Even black holes might use entanglement to preserve information, as suggested by the ER=EPR conjecture, a bold idea that equates wormholes with entangled particles. The implications ripple outward. Future quantum networks could leverage entanglement for unhackable communication, while quantum computers might exploit these non-local links to solve problems no classical machine could crack. But the deepest revolution could be philosophical. If space-time isn't the bedrock of reality, but something that emerges from quantum weirdness, we're standing at the edge of a paradigm shift as profound as relativity or quantum theory itself. The spookiness isn't just in the action, it's in realizing how little we truly grasp about the stage we call the universe. Imagine an invisible puppeteer controlling the cosmos, its hands unseen, but its influence undeniable. That's dark matter, the universe's most elusive architect, shaping galaxies and bending space-time with gravity alone. While it emits no light, absorbs no radiation, and interacts with ordinary matter only through gravity, its fingerprints are everywhere. Take spiral galaxies like our Milky Way. Their outer stars whirl around the center so fast that they should fling into the void, yet something invisible holds them in place. The math is clear: without the gravitational grip of dark matter, galaxies would tear themselves apart. This cosmic glue doesn't just stabilize individual galaxies, it sculpts the universe's largest structures. Picture the cosmic web, that vast network of galaxies strung along filaments like pearls on a necklace. Simulations show that without dark matter's gravitational scaffolding, these filaments wouldn't exist. Ordinary matter, the stuff of stars and planets, accounts for only 15% of the universe's total mass. The rest, a shadowy sea of dark matter, its gravity carving valleys and peaks in space-time where galaxies cluster like cities around invisible highways. Some of the most striking evidence comes from gravitational lensing, where dark matter's gravity warps space-time so severely that it distorts light from distant galaxies. Astronomers can map its distribution by studying these cosmic funhouse mirrors, revealing halos of dark matter far larger than the galaxies they host. The Bullet Cluster offers a dramatic example. Two galaxies collided, their dark matter plowing ahead while visible gas lagged behind, leaving a gravitational ghost visible only through its bending of starlight. Yet the mystery deepens. If dark matter bends space-time, could it also warp time itself? Some theories suggest dense clumps might create localized time distortions, though we've yet to detect them. Others propose exotic particles like WIMP or actions as dark matter's building blocks, but decades of underground detectors and particle colliders have come up empty. One thing's certain: dark matter is the silent choreographer of the cosmos, its gravity orchestrating the dance of galaxies while remaining forever out of sight. Until we uncover its true nature, we're left tracing its shadow, a reminder that the universe's greatest forces might be the ones we can't see. What if everything you know, every memory, every sensation, even the universe around you isn't real, but just a fleeting hallucination of a lone, disembodied brain floating in the void? This is the Boltzmann brain paradox, a thought experiment so unsettling it makes the Matrix look tame. named after physicist Ludwig Boltzmann, who first grappled with how order emerges from chaos. The paradox takes probability to its logical extreme. If the universe tends toward disorder over time, as thermodynamics insists, then the most likely, ordered state isn't a vast, structured cosmos, but a single, self-aware moment conjured by pure random chance. Picture this: in the infinite expanse of space, given enough time, quantum fluctuations could theoretically arrange particles into a fully formed brain, complete with false memories of a past that never happened. It's like shaking a box of Scrabble tiles for eternity and suddenly spelling out the complete works of Shakespeare. According to the math, the odds of a Boltzmann brain popping into existence are astronomically low, but in an infinite universe with infinite time, astronomically low doesn't mean impossible. It means inevitable. The implications spiral into existential vertigo. If Boltzmann brains are more probable than entire universes, how do we know we're not one of them? Your childhood, your favorite meal, even the screen you're staring at right now, all could be a phantom narrative generated by a mindless quantum accident, dissolving as quickly as it formed. Scientists recoil from this idea not because it's impossible, but because it's too possible. If reality is just a statistical fluke, why does the universe appear so consistent? Why do the laws of physics hold steady instead of flickering like a dying light bulb? Some theories push back, suggesting the universe's low entropy beginnings, like the finely tuned conditions of the Big Bang, make Boltzmann brains vanishingly unlikely compared to a sustained, coherent cosmos. Others argue that consciousness itself might be impossible without an external world to ground it, like a computer that can't run without hardware. But the paradox lingers, a ghost in the machinery of physics, forcing us to confront the unnerving possibility that reality's foundation might be shakier than we ever imagined. Perhaps the most haunting twist: the Boltzmann brain isn't just a sci-fi nightmare, it's a mirror. If we can't prove we're not random fluctuations, then certainty itself becomes an illusion. The paradox doesn't just question the universe, it questions the tools we use to understand it, leaving us adrift in a sea of probabilities where even the act of doubting might be part of the mirage. We've always thought of time as a steady, unshakable river flowing from past to future with unbreakable certainty. But peel back the layers of reality, and that river might not be so deep after all. In the quantum realm, where gravity meets the subatomic, some of the most radical theories suggest time isn't fundamental at all. Instead, it could be an illusion, emerging from a timeless sea of more primitive building blocks, like temperature emerging from the chaotic dance of molecules. Imagine a clock with no hands, yet still somehow keeping time. That's the paradox physicists wrestle with when they try to reconcile quantum mechanics and general relativity. Take loop quantum gravity, a leading theory attempting this unification. At its core, the universe isn't made of smooth, continuous space-time, but tiny, indivisible loops. Think of a fabric woven from threads so fine they're imperceptible until you zoom in. Here's the catch: time doesn't appear in the fundamental equations. It's not that time doesn't exist in this framework. It's more like realizing the story you're reading wasn't written in ink, but etched into the grain of the paper itself. Time emerges from the interactions of these loops, a collective effect rather than an independent dimension. It's as if the universe runs on a cosmic blockchain, with each block representing a discrete quantum state, and time is just the sequence in which we perceive those blocks updating. This idea flips causality on its head. If time isn't fundamental, then cause and effect might not be as ironclad as we think. In our everyday world, a glass shatters because you dropped it. Cause precedes effect. But in a timeless quantum landscape, the glass's shattering and your dropping it could be entangled events, linked not by a timeline but by deeper, more abstract relationships. Some models even suggest that at the Planck scale, the universe's smallest possible length time could stutter, flickering in and out like a faulty light bulb, with events happening out of sequence until they average out into the smooth flow we experience. The implications ripple outward. If time is emergent, then the Big Bang wasn't just the beginning of matter and energy, it was the moment time itself started ticking. Before that, the concept of before might not even apply. It's like asking what's north of the North Pole. The question loses meaning. Some physicists speculate that in this pre-temporal state, the universe existed in a superposition of all possible configurations, a quantum foam of potentialities without sequence. Only when gravity and matter reached a certain threshold did time crystallize out of the chaos like ice forming on a pond. But how do we test something so abstract? Clues might lie in black holes or the early universe where quantum gravity effects dominate. If time disappears near a singularity, as some models predict, it could leave imprints in gravitational waves or the cosmic microwave background anomalies that don't fit the smooth, time-bound universe we know. Others hunt for quantum fluctuations in space-time itself, looking for tiny, fractal irregularities that betray its discrete, emergent nature. This isn't just philosophy, it reshapes how we understand reality. If time isn't foundational, then free will, entropy, even aging could be side effects of a deeper, timeless machinery. It's a humbling reminder that the universe doesn't owe us intuitive explanations sometimes. The truth is stranger than the stories we tell to make sense of it. And if time is indeed an illusion, it's one so convincing we've built our entire existence on its fleeting fabric. The eerie silence of the cosmos isn't just puzzling, it might be hiding a fundamental truth about space-time itself. Enrico Fermi's famous question, "Where is everybody?" takes on a new dimension when you consider that advanced civilizations could be operating on scales we can't even perceive. Imagine ants scurrying across the forest floor, oblivious to the highway roaring just beyond the trees. To them, the world is dirt and leaves, but to us, it's a vast network of roads and cities. What if we're the ants, missing entire layers of cosmic traffic happening right over our heads? One possibility is that intelligent life has already mastered space-time in ways that render them invisible to our primitive tools. Wormholes, for instance, could serve as interstellar shortcuts, allowing civilizations to bypass the tedious crawl of light-speed travel. Instead of broadcasting radio signals across the void, a method we've been relying on for barely a century, they might communicate through quantum-entangled networks or manipulate gravity itself to send messages. These aren't just sci-fi tropes, they're plausible extensions of known physics. If a civilization can stabilize a wormhole, why would they waste energy beaming signals into the dark when they can step directly into another star system? Then there's the mind-bending idea of higher dimensions. String theory suggests our universe might be a three-dimensional brain floating in a higher dimensional space. Advanced beings could have evolved beyond our brain, accessing dimensions where gravity and light behave differently. To them, our frantic searches for radio waves or Dyson spheres might look quaint, like trying to text someone using smoke signals. Even their megastructures, if they build any, could exist in spatial dimensions we can't see or comprehend, leaving no trace in our observable universe. But the most unsettling answer might be temporal. Space-time isn't just a stage, it's a dynamic, evolving entity. Civilizations rising and falling over billions of years might rarely overlap. Imagine two candles burning in a vast, dark room. One flickers out just as the other ignites. The universe is 13.8 billion years old, and Earth's technological era spans less than a blink. We could be alone not because life is rare, but because we're tragically out of sync, cosmic ships passing in the night, separated by eons rather than light years. Or perhaps they're already here, woven into the fabric of reality itself. If consciousness can emerge from the quantum foam or higher dimensional physics, aliens might not be out there at all, but embedded in the very structure of space-time, as fundamental as gravity. The Fermi paradox isn't just about missing radio signals, it's a mirror. reflecting how little we understand about the universe's true possibilities. Until we crack the codes of wormholes, dimensions, or time itself, the silence might not be emptiness, but a language we're not yet equipped to hear. There's a force lurking in the void that makes black holes look gentle, an unseen energy so relentless it could unravel the universe atom by atom. Phantom energy, a hypothetical dark energy on steroids, doesn't just accelerate the expansion of space-time. It dials that expansion up to infinity, triggering a doomsday scenario called the Big Rip. Picture this: trillions of years from now, galaxies aren't just drifting apart. They're being wrenched apart by space itself, stretching at speeds beyond comprehension. First, galaxy clusters snap their gravitational bonds, flinging members into the void. Then, individual galaxies shred like tissue paper, stars torn from their orbits. But the horror doesn't stop there. In the final months, phantom energy's grip tightens. Planetary systems disintegrate as the space between planets expands faster than gravity can hold them. Earth would float away from the sun, not in a graceful spiral, but in a violent snap, as if space-time itself were made of overstretched rubber. Then, in the last hour, the terror reaches atomic scales. The very fabric holding matter together, the forces binding nuclei to electrons, quarks inside protons, loses the battle against the expanding void. Atoms explode silently, their pieces hurled into an ever-widening nothingness. By the end, even space-time's structure might fracture, leaving a desolate, empty cosmos where the concept of distance no longer has meaning. What makes phantom energy so unsettling is how it inverts our intuition. Dark energy, which currently drives cosmic acceleration, behaves like a gentle pressure, but phantom energy grows stronger as space expands, creating a feedback loop of destruction. The more space stretches, the more phantom energy dominates, stretching space faster in a cycle that spirals toward infinity. Some theories suggest this could happen in as little as 22 billion years, a blink on cosmic scales. The irony: phantom energy's existence would solve one mystery while creating another. It fits observations of the universe's accelerating expansion, but its ultimate implications are apocalyptic. For now, it remains a mathematical specter in cosmological equations, a reminder that the universe's fate might be far stranger and more violent than we ever imagined. What if the universe isn't just governed by the laws of physics, but by lines of code? The simulated universe hypothesis isn't just a sci-fi trope. It's a serious scientific argument that our reality might be an artificial construct running on some unfathomable computer. At its core, this idea hinges on a provocative question. If space-time has fundamental limits, like the Planck length, where reality itself seems to pixelate, could those limits be the telltale resolution of a cosmic simulation? Think of it like playing a video game. The more you zoom in, the more you notice the jagged edges of polygons or the finite textures, artifacts of the game's underlying code. If our universe has similar pixels, could they be glitches in something far grander? Take quantum mechanics, where particles exist in blurs of probability until observed, almost like a computer rendering details only when a player looks. Or entanglement, where particles instantly coordinate across vast distances, defying space-time. These aren't just quirks, they're exactly what you'd expect if reality were optimized to process only what's necessary, like a game engine loading assets on demand. Even the speed of light could be a built-in processing limit, preventing the simulation from overloading. Philosopher Nick Bostrom formalized this in 2003 with his trilemma. At least one of these must be true. Either civilizations never reach post-human stages capable of running ancestor simulations, they choose not to, or we're almost certainly living in one. Given the explosive potential of computing power, the third option starts to feel uncomfortably plausible. Elon Musk famously quipped that the odds we're in base reality are 1 billion to 1. And the evidence isn't purely philosophical. Some physicists hunt for rounding errors in the fabric of reality, tiny anomalies in high-energy particle collisions or cosmic rays that might reveal the universe's computational underpinnings. Others suggest that if space-time is pixelated, certain wavelengths of light could carry imprints of its lattice-like structure, like seeing the grid behind a digital painting. Yet the most haunting implication isn't technical, it's existential. If we're in a simulation, who's running it? Are we someone's forgotten experiment, a cosmic game of The Sims, or layers deep in a simulationception of nested realities? The hypothesis doesn't just challenge our place in the cosmos, it redefines what real even means. And until we find those cosmic glitches or hit the universe's debug mode, we're left staring at the stars, wondering if they're just someone else's pixels. Could the very act of observation twist the fabric of reality? This isn't just philosophy. Quantum mechanics already shows us that particles exist in blurred states of possibility until measured, as if the universe hesitates until someone looks. Now, fringe theories take this further, suggesting consciousness might not just interpret space-time but actively shape it. Imagine a cosmic version of the observer effect where the universe's structure, its bends, its flow, even its existence depends on minds to pin it down. The idea builds on the quantum measurement problem. In classic experiments like the double slit, particles behave as waves when unobserved, creating interference patterns. But the moment you measure which slit they pass through, they snap into definite positions, as if the universe recalibrates based on attention. Some interpretations, like the von Neumann-Wigner hypothesis, propose consciousness itself triggers this collapse, turning fuzzy probabilities into concrete reality. Extend this to space-time, and you get a wild implication. Without observers, the universe might not just be indeterminate, it could be incomplete, like a movie reel waiting for a projector's light. This bleeds into panpsychism, the view that consciousness is a fundamental property of the cosmos, like mass or charge. If true, space-time might not be a static stage but a dynamic interplay between matter and mind. Think of it like a dream. The dreamer and the dreamscape aren't separate, one conjures the other. In this view, black holes or distant galaxies could exist in unresolved potential states until some form of awareness, human or otherwise, interacts with them, even indirectly. Critics dismiss this as mysticism masquerading as physics. After all, why privilege human consciousness? A rock or a photon could observe just by interacting with another particle. Yet, some models in quantum cosmology flirt with these ideas. The participatory universe principle, inspired by John Wheeler, suggests reality emerges from a network of observations stretching from the Big Bang to today, like a cosmic game of telephone where each measurement narrows the possibilities. Even the famed delayed choice experiment hints at this. Particles seem to decide their past behavior based on future measurements, as if time itself is a feedback loop shaped by observation. The wildest twist: if consciousness molds space-time, then the universe might be a self-contained loop. Observers need space-time to exist, but space-time might need observers to crystallize. It's the ultimate chicken and egg paradox, where the cosmos and the mind co-create each other. While mainstream physics still treats this as speculative poetry, it forces a humbling question. Are we just passengers in the universe, or silent architects weaving reality with every thought? From wormholes stitching the cosmos together like cosmic thread to the unsettling possibility that reality might be a hologram projected from the edge of space-time, the universe has proven itself far stranger than fiction. We've seen how black holes drag the fabric of reality around them like cosmic whirlpools, how time itself slows to a crawl under gravity's grip, and how quantum entanglement defies space and distance entirely. Each of these discoveries isn't just a curiosity, it's a crack in the foundation of what we thought we knew, forcing physicists to rewrite the rules of reality itself. Consider the implications. If wormholes exist, even theoretically, the universe could be threaded with hidden shortcuts, turning billion light-year journeys into a single step. If the holographic principle holds true, everything you see, touch, and experience might be a shadow cast by information encoded on some distant, two-dimensional surface. And if time is an illusion emerging from quantum interactions, then the past, present, and future could be as fluid as the particles that make up your bones. These aren't just thought experiments, they're frontiers where science grapples with the unimaginable, where equations hint at truths that defy intuition. What makes these mysteries so electrifying isn't just their strangeness, but how they reveal how much we still don't understand. Dark energy, phantom energy, the great attractor. Each one is a cosmic puzzle piece that doesn't quite fit, challenging us to rethink gravity, matter, and the very structure of space-time. And let's not forget the Fermi paradox's haunting silence, which forces us to ask whether we're alone or simply blind to civilizations operating on scales we can't yet perceive. So tell us, which fact bent your mind the most? Was it the black holes spinning space-time like a top, or the chilling idea of vacuum decay rewriting the universe in an instant? Drop your favorites in the comments, and if you're hungry for more deep dives into the cosmos, hit subscribe. The universe is vast, mysterious, and far from done surprising us, and neither are we.